The instruments that we've dealt with so far have been wind instruments. We did the law of closed pipes and the law of open pipes. But today we're going to talk about the law of strings and stringed instruments such as guitar. And as I've been demonstrating, if you've been absent from class and you're watching this, I demonstrated this in class. You have a guitar. I have a guitar right here. And the strings vibrate at a certain frequency, and I can manipulate those frequencies by shortening the string, tightening the string, okay, and then playing the strings in different all together in different combinations to make chords. That's a D right here, D chord. I think this is D sharp. And it's fun. It's gorgeous stuff. And you should all understand it. So, here's the first thing you need to know. Here's a string. Like this would be the bridge of the guitar, and maybe this up here's the fretboard. And so here's the string, just all by itself. Now, if you were to send a little pulse through the string, it would move with a certain velocity. So it's going to have a velocity, and the velocity of the speed of the pulse in the string is equal to the frequency of the sound that you're making times the wavelength. I mean, this has been true for all the waves and so on that we've been studying. This is true for it, okay? But here's what's different about the law of strings over the law of open and closed pipes. What was the velocity in pipes? What velocity did we use for the wave? We used 343 meters per second because what was waving, what was physically resonating in the pipe was sound itself. Okay, so the velocity of the waves was the velocity of sound. And so you would just use the speed of sound. Now, with strings, this velocity is the velocity of a pulse in that string. So it's not the speed of sound anymore. So for the law of strings, you should write this down, V does not equal the speed of sound. It can be greater or less than the speed of sound, but it's not the same as the speed of sound like it was with the law of pipes. So they have to give it to you or you have to solve for it, okay? And so on. Okay, so if you know this, maybe they'll give you this and you can, do this. Now, what if I had set up a series of waves? And by the way, notice too that I have a pulse here, and that pulse has a certain amplitude, doesn't it? And how do I play the string? I pluck it, right? And I disturb it in a direction that is perpendicular to the direction of the wave itself. What do we call waves where I disturb the material perpendicular to the direction of the wave motion? We call those transverse waves. So what I'm setting up in the string is a transverse wave, not a longitudinal wave. Now this string will vibrate against the air, and it will vibrate against the sounding board of the guitar, and that will vibrate against the air at a certain frequency. And then those waves come off the guitar as longitudinal waves moving at the speed of sound, because it is producing sound. But don't confuse the speed of the wave in the string by setting up a transverse wave in the string with the longitudinal wave set up in sound, in the air, that's moving at the speed of sound. Okay, there are different things going on. Okay, so what we did is we said, well, what's the lowest possible frequency in a guitar? Well, it happens with, if the string is at rest like this, but then you pluck it right in the middle, and it sets up a wave that if you looked at it under a strobe light, and by the way, we are going to look at guitar strings under strobe lights, hopefully on Friday. I'll do it before you seniors leave, though, because I want you to see it. It's very cool. Now, I'm exaggerating the displacement, because if you tried to make a guitar string vibrate this much, you're probably going to break the string. But let's exaggerate the amplitude so we can actually see it. Okay, this is moving back and forth like this with a certain amplitude, transverse wave. But how much of a wavelength is this right here? I mean, what would a full transverse wave look like? A full transverse wave would look like this. It would go up, and then what does it do? It would go down like this. Let me move that over. See? But it's not, it can't go here because there's no string right there. The string is from here to here. So how much of a full wave is this shape right here? How much of a wavelength? Well, if this is a full wavelength from here to here, this would be how much of a wavelength? Half a wavelength. So the wavelength of the sound, and we're going to call this L. So what's the relationship between the length of the string and the wavelength of the wave in the string for this first frequency? Well, the length is equal to half of a wavelength, because this is a full wavelength of the sound, or not of the sound, of the wave in the guitar string. It would go up and down like this, right? Well, what we want to do is relate the frequency that we hear to the length of the guitar string. And so we could say, well, look, velocity equals frequency times wavelength. So I can solve for wavelength. Wavelength equals velocity divided by frequency. So L equals velocity over twice the frequency. But what I really want is, I want the frequency as a function of the length of the string. So I'm going to solve for it. Let's solve for F here. So that means that F and F1, this is the lowest frequency that will resonate in a guitar string or a violin or any stringed instrument. F1 is equal to the velocity of the wave in the string. This is not the speed of sound. No, 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 not the speed of sound. This is the velocity of the wave in the string is equal to, it's the velocity divided by 2L, twice the length. Okay? Now, I can do a trick with the guitar string. I can make the frequency twice as high, and I'll demonstrate that. Now, if you're watching the video, you won't be able to see this because I can't get the whole, well, maybe I can get the whole guitar in there. I don't know. Let's see what happens. Here's my guitar. Okay, that's ridiculous. But here's the lowest string. That's F1. Now what I'm going to do is I'm going to put my finger in the very center of this string and then pluck the string. Okay, and it sounds higher in pitch. So here's what I was physically doing. If this was the guitar string, I would put my finger on the center of the string. So let me actually draw this. I would put my finger on the center of the string right here, and I would not allow the string to vibrate at this point. And so the string would, when I pluck the string, it would set up a wave in the string that looks like this. So it vibrates. Here's the string when it's at the equilibrium position. This will be online if you want to watch the rest of it. Okay, and it goes up and down, but it doesn't move right here. Now, what do we call the place on a string that doesn't move? We have a name for that. We've talked about it before. What's it called? It's a node. So we have a node right here and a node right here. And then what do we call the place of maximum displacement for the string? It's called an antinode. How imaginative, huh? We have nodes, and then we have antinodes. Antinode is where the maximum displacement happens. Well, when I did this with the guitar, right, I forced a node to exist in the very center. So there's a node right here. So over here you had two nodes. Now you have three nodes. 1, 2, and 3. Places where the string is not allowed to move. Now let's relate the length of the string to the wavelength of the wave moving in the string. And do you see that if the wave looks, let's freeze it right here, it goes up and then down. Do you see that's a complete wavelength, isn't it? That makes a complete sine wave. Right? So do you see that the length of the string is equal to the wavelength of the not of the sound, but of the wave in the string, the transverse wave that's in the string. Oh, okay. Well, now we can use this relationship again and say that the length is equal to the velocity over the frequency, because wavelength equals velocity over frequency. And so therefore, I can say F2, and this is the second frequency that will resonate with this string. The second frequency is equal to V over L. But do you see that this is the same thing as 2V over 2L? What if I put a 2 here and a 2 here? That's okay, isn't it? But what is V over 2L? That's F1. So this is equal to 2 times the first frequency. And that's what we heard when I plucked the string in the guitar. I plucked the string at its lowest frequency. That's F1. Then when I held my finger in the center of the string and plucked it, I got something that was an octave higher. Well, now I can just do the same thing. Am I still on camera? Yeah. But now what I can do is place my finger on the string about I didn't draw that very well, about a third of the way down. And it sounds like this. Okay, here's the full string. Right there. I'm holding my finger down a third of the way down the length of the string, and it makes a higher pitched frequency. Higher frequency. And why is that? Well, when I hold my finger here, I force a node onto the string. So the string will now vibrate like this, and like this. And I'm forcing the guitar string to do this. Now, by the way, the amplitudes of the transverse wave in the string is greatly exaggerated here. It's more like what I did when I was vibrating that spring. Okay? But it does move a little, you know, it is moving. It's very fast. Now, look at the relationship between the wavelength and, see, here's the length. Now, how much of a wavelength, how many wavelengths do I have here? Well, here's half a wavelength, one full wavelength, 1.5 wavelengths. You see the distance between the nodes, is half a wavelength, right? So here I have 1, 2, 3 halves of a wavelength, or 3 over 2 times the wavelength. Well, that means that L is equal to 3 over 2 times the velocity of the transverse wave over the frequency, which now means I can solve for the frequency, and that frequency will be F3. And F3 is going to be equal to 3 over V over 2L. All right? But what is V over 2L? That's F1. So this is going to be 3 times F1. So up here you have 1 times F1, 2 times F1, 3 times F1. What do you think the next one's going to be? I think it's going to be 4 times F1. Let's find out. All right. Now, if I hold my finger 1/4 of the way down the string, okay, let's see, here's, and then, I think that's it right there. You're going to get a higher frequency resonating on that string. So if here's your guitar string, and let's see, here's halfway, here's 3/4, here's a, so you hold your finger right here, you force a node to vibrate there. So now the string will go up, down, and up. Again, I'm greatly exaggerating the amplitude here. So it's going to go like this. I'm not drawing this very well, but sorry. So you're going to get 1, 2, 3, 4, 5 nodes, and 1, 2, 3, 4 antinodes. And the length here is 2 complete waves, or twice the wavelength, which means that L is equal to 2 times the velocity over the frequency. If I solve for the frequency, I'll call this F4. I'm going to get 2 times the velocity over the length. But if I multiply both top and bottom by 2, okay, and I look at this, velocity over 2L, that's F1, and what is 2 times 2? It's 4. Am I on screen? Yeah, 4 times F1. So if I look at the whole thing here, let me zoom out. I can force the guitar string to vibrate at its fundamental frequency, and then at a frequency that's twice as great, or 3 times as great, or 4 times as great as that fundamental frequency. And that's what I can do with the string. Now, there's other things I can do. Like if I want to change the frequency, okay? Now, actually, let me get to the overall formula here. So what can I say is true about F sub n? If I'm going to write a general formula for the frequency that resonates on a guitar string, well, n is any integer, right? N is going to be equal to 1, 2, 3, 4, etc. Okay? Well, what am I going to write here as my formula in terms of the velocity of the transverse wave and the length? The frequency is going to be a function of the length. Well, first of all, it's just, look, n, 1, 1, 2, 2, 3, 3, 4, 4. So n, it's just going to be, like, if I want the third frequency, I just multiply by 3. And then it's going to be the velocity of the transverse wave over twice the length of the guitar string. Now this tells me, if you're a guitar maker or a guitar player, this tells you how, what you're doing when you change the frequency that a string will vibrate at. There's 2 ways to do it. You can change the length of the string, and that's what you do when you use the fretboard. Okay, if I place my, here I'll play the string. Okay, what am I doing? I made the string shorter. Why? Because now it only vibrates from where my finger is pressing it down to the bridge. Even shorter. Okay, so you can change the length. The shorter the length, you're dividing by a smaller number, so you get a higher frequency. Makes sense. Okay? Then you can control the speed that the wave travels in the string. How do you control the speed of the transverse wave? By tightening or loosening the string. Well, first of all, you can have a different string. Like, this is the high E on a guitar. Whoops. Now, this is the little skinny string, right? Let me show it underneath here. Here's the little skinny string. All right? And it has very low mass compared to this big thing. Big string, lots of mass. You got to move lots of mass back and forth. So it's that additional mass makes it vibrate at a lower frequency, right? Or you can tighten the string. If you tighten the string, you actually increase the velocity, right? I just tightened it. I don't want to make it too tight. I want to break the string. See, I'm loosening it. Now the string's really loose. So there's not much tension in the string. So there's not much force trying to pull it back and forth. There's not as much force, so it takes more time to pull it back and forth. So if you increase the mass of the string or the density, it's going to vibrate slower. Or if you decrease the tension, you're going to make it vibrate slower or lower frequency. Okay. So this is the general formula for the law of strings. If you know this formula, and of course our standard velocity equals frequency times wavelength, you can solve any problems. Now here's the only confusing part about the law of strings. Okay? This is the velocity of the transverse wave in the string. But sometimes they'll give you the frequency of sound and ask you for the wavelength of the sound. So sometimes you'll have to go V sound equals frequency times wavelength. Now here we have two equations that look very similar. The frequency of the string will be the same. The frequency here and the frequency here are the same. But the wavelength of the transverse wave in the guitar string will be different than the wavelength of the longitudinal wave of sound. So these guys, I should put a sub-sound in there. So you got to be careful when you're working with the problems with the law of strings. Am I talking about sound, or am I talking about the wavelength of in the string? Am I talking about the speed of sound, or am I talking about the speed of the transverse wave in the string? So keep those straight when you're solving these law of string problems, okay, and you'll be fine. Okay, that is all.